at the University of Utah, but I'm from here, so I'm glad to be back. That would be turn on button. Awesome. Yeah, so like I said, as my bio says, I've been teaching at the University of Utah, so I'm glad to be back here where I got my degrees. So let's get going. So just a little bit about Hand Sound Loose. Hand Sound Loose has been around Utah since 1974. So right after BYU, I went to Hand Sound Loose, and I've been there ever since. It's been a great career. They're an awesome company, and if anybody's interested in what I'm talking about, we're always looking for bright students to hire. So just a few of our spattering of projects. Mostly water resource engineering, but we do most aspects of civil engineering. We already talked about that. So this water system optimization is something I kind of fell into. My first assignment going into Hand Sound Loose coming out of this seminar was hydraulic modeling. Started using software that models water systems. And so I'm going to talk about today is water system optimization, something I developed over my 18-year career. So there's lots of water in the world. The problem with the water is it's usually in the wrong spot and in the wrong quality to drink. And so we have to move it, treat it, and deliver it to those who need it. And there's lots of processes along the way that we as civil engineers are involved with. Treating the water, moving the water. After you use it, you put it back and you treat it again, and then you put it back into the environment, and then you pump it out again, and around and around it goes. And it takes energy to move and treat water. So there's this, what they call the energy water nexus. I'm going to be talking about the energy for water component, but it also takes water to create energy. So they're intertwined. So I'm going to be focusing on the energy for water component. So how much energy does it take to deliver a unit of drinking water? Well, the answer is it depends. Every single water system is different. Even Orem versus Provo, systems right next to each other can be completely different. So it depends. We've been doing some research about how much energy it takes a community to deliver drinking water. So this is just a little spattering chart. The red dot indicates intensity, green is lower energy intense, red is higher energy intense, and then the size of the dot is how much water is delivered. So you can see the Los Angeles area, the dots are big, but they're also red, meaning it takes a lot of energy to deliver that water. Whereas you go look in the New York area, there's a lot of green dots, and that's because they take advantage of gravity to deliver their water. So they use less energy. Overall, there seems to be this sweet spot of where it takes about so much energy to deliver water. But what I found through my career is that you can't really look at a water system and compare it to another one. Like I said, it depends. And so unlike buildings where you look at energy efficiency and you can look at one building and compare it to another because there's similarities, in water systems you can't really do it that way. You've got to look at the individual water system and compare it against itself. So the ones that are on the higher side, so this would be the Los Angeles area, they use a lot of energy, but that doesn't necessarily mean they have more opportunity to save energy than the ones that use not a lot of energy. Again, every water system is unique, and in fact, the ones that use not a lot of energy, usually they have some benefit, and sometimes they're not taking full advantage of that benefit. So those guys could actually have more capacity to save energy than the ones that have higher energy intensity. So this is not for you to read, but this is just a bunch of quotes about national organization, international organizations that have studied the inefficiency of water in systems. So this is all theoretical. This is not from them actually saving energy. This is them looking and seeing, well, how much energy could be saved? And generally they say it's 10 to 30%. And this data is getting old, probably 10, 15 years old now. But what I've been able to see, being in the trenches and actually saving energy, we're seeing the same thing. 10%, even up to 49%, meaning a water system is using twice as much energy to deliver clean water to the customers than they really need to. And this is real data. So water system optimization, why do it? So when I started to do this 10 years ago, how it happened is I started to look at my hydraulic models and seeing interesting things. Water pumping around in circles, things that didn't make sense to me as being efficient. And so I started to do what I call system optimization. And over time, trying to tell people what it was, trying to get people to look at this thing was a hard task. There was lots of barriers. But nowadays it's getting easier because I have those results. I can show people those results and they're excited. So here's some of the reasons why water systems engage these days: reducing operating costs, shrinking environmental footprint, improving the public acceptance, improve the level of service and water quality. It's cool to be sustainable, and this is a big step in that direction. So here's a little Venn diagram that I developed several years ago to try to explain what we do or what a optimized system is. So obviously, job number one for water system is to deliver high quality water and at the proper pressures. That if we add the energy component in there, the reason why we add the energy component is because it's so expensive. So if we can save energy, we can save money, but we can't affect the water quality or the hydraulic performance of the system to do that. The exciting thing, though, is when we look into a system and try to find ways to save energy, the water quality and the hydraulic performance component isn't necessarily opposing forces. A lot of times, because we're looking at ways to save energy, we also find ways to improve the water quality and improve the hydraulic performance. So in the end, they save money because they're using less energy, and their system actually runs better and delivers higher quality water to the customer. So it's a win-win solution all the way around. So usually in the system optimization process, it's not just a one-and-done type of thing. It's ongoing. You get a footprint. You can't measure success unless you know what you're doing to start out with. So a baseline energy and water footprint. Energy efficiency opportunities are identified, and then you prepare the optimization plan, you engage the stakeholders, and then you execute, and then you measure, and then around and around you go. It's a never-ending process to keep improving your system. So some of the tools and strategies that we use, one thing are engagement programs. So like I said, one of the biggest barriers were the people themselves. It's just something they do, and they didn't want to change how they were doing it. And so actually behavior training goes a long ways to saving energy. Lately, most of these engagement programs have actually been paid for by the power companies. So the power companies hire me to go into a water system and help them save energy. It's a place where the energy companies couldn't go because they didn't understand water systems, and the water systems would say, no, we use this much energy, we can't affect our water quality or our hydraulic performance, so go away. So they hire us who understand water systems to help the people that run them understand how they can save and improve their hydraulic performance and improve their water quality. And so then it becomes a win-win situation for the power company. And the reason why the power company wants to pay me to find energy efficiency is because it's the lowest cost way to get more capacity into the system. So these are the costs of putting wind, natural gas, coal, nuclear, biomass, it's very expensive, and these costs keep going up every day. And so to pay me to find waste, it increases their capacity. And the water systems get this because they do the same thing. They have programs to get people to save water, to use less of their product. It's kind of counterintuitive, but in civil engineering, that's our profession, which I enjoy, is that we do things that are on the base level of civilization, delivering water. So we want to save water, we want to save the natural resource, we want to save energy. Well, on the flip side, civil engineers, we waste energy too, because we are a little bit too conservative. I'll get to that. So another tool that I use is hydraulic modeling. Like I said, that was one of the first tools that I got into, and this is how I understood that there was this opportunity. So hydraulic models are wonderful. They're becoming more and more just part of how you do business as a civil engineer, as a water system. Before, you couldn't really see into the water system, and now it's becoming an invaluable tool to make systems more efficient. So the water model actually models those three pillars you saw in the Venn diagram. It models energy, it models hydraulic performance, and it models water quality. So with the model, and with all the system components in place, I can measure all three of those components, and that's how we can tell that an opportunity will help the system and save energy before it's actually even implemented. So energy efficiency, water quality. So the basics of hydraulic modeling, basically you have 6 components. So it's like Legos. I enjoyed Legos growing up. My kids have lots of Legos. Hydraulic models are similar. You just have these 6 components, but with these 6 components, we can put together a model of any water system in the world. That's all you need, are these 6 components. A reservoir, a pump, a tank, a pipe, a valve, a node. You put them together in the right order and give them the right parameters. Now it's not perfect, but it's like this. This is all made out of Legos. When you step back, it actually looks pretty good. You look too close, and it looks a little messy, but you step back, and it does a marvelous job of helping people understand their water systems and helping the engineer understand what the opportunities are. So here's my little example of extended period hydraulic modeling. So at first, when I first started, most of the hydraulic modeling was static. So you'd pick a worst case scenario, low pressure time or high pressure time, and you take a snapshot and kind of assess what's going on. It gave us some data, but it's not as powerful as extended period modeling. Extended period modeling is more like a movie. So a movie, it's a set of still shots put together and then played back to show motion. And so that's kind of how the hydraulic model works. It's a set of static models put together. So you take a static model, and then you run it, and then you take the results and run it again at the next time step, and then again and again and again and again. And then once you've done that, then you can play it back so that you get a sense of the system working. So you can see the tanks filling and emptying. You can see the water where it's going into the system, and that gives the operators and the engineers good confidence that the solutions are working. So another thing that we've been working on, actually with Aquaveo, I came to Aquaveo because I needed a solution to deliver an easy platform for the operators and administration engineers of a water system to be able to use their model. So this platform is HTML based, and they can look at their model on a phone or an iPad or a computer, wherever they are in their system. I don't have a lot of time to talk about this, but it's exciting. And we've also added analysis tools that we can throw a hydraulic model into the computer, and it can identify inefficiencies, and then we can go look at those. But having the computer make us a list that we can go after is powerful. One really simple way that we save energy in water system is just source prioritization. For every component that uses energy, whether that be a pump station, a treatment plant, a well, we identify what energy it takes for that process. And then we make a list of those in the system so that we understand, should we use well 5 first or well 3? Well, if there's no difference in water quality or other parameters, let's use well 3 or well 5 or well 1, it's even better. And in this case, the CWP is a treatment plant. Let's maximize the treatment plant instead of using some of the wells. So there's a large system in Utah, Jordan Valley Water Conservancy District. They serve basically wholesale water to all of Salt Lake County. Basically their first year, that's all they did. We did very little hydraulic model. All we did was modeling. All we did was rate all of their sources, and they picked different sources than they ever had before. And in their effort, they've saved about 19%, which is equivalent to about 20 million kilowatt hours. This gets very significant. And in the end, their system actually runs better. So the power company's happy. They bought those kilowatt hour capacities. That's a lot of capacity. So that's yearly that they're saving. And they're continuing on to do other things, but simple things like just recognizing how much energy a certain source within your system can be powerful. There's actually a journal article in AWWA this month that we did that is a case study for Jordan Valley. So one of the more common things that the power companies would do is just equipment audits, equipment upgrades. Yeah, we get to those, but what I do is more holistic. We look at the whole system, and yeah, maybe that source is pretty efficient, but if we can turn it off, that's even better. So water system optimization, we can get into the details, but it's really a holistic view. And then if you can, SCADA is a way to automate your system and see what's going on. But if you can automate the most efficient, identify it, and then automate the most efficient way of running the system, that's powerful. If you have to default to something else because something's going on, that's fine. But then if it goes back automatically to the most efficient, it's like having the automatic lights in the room. And then tracking. Usually we call this an energy model, but we, again, identify the baseline, and then we track how they're doing. And so in this case, the water demand is going up, usually because that's growth. But over that same period of time, their energy use is going down, which is a good thing. So tracking is a way to understand how much energy you're saving. So something I teach to water systems are these 5 common inefficiencies that we find in lots of water systems. And we did a little alliteration with L's: looping, leaping, leaking, losing, and loading. I'll just go through them really quick. Loading is when you use energy to meet your peak rather than using storage. So if you look around in the valley, you see lots of storage tanks, or anywhere that has water, there's usually a storage tank. Those storage tanks could be seen as batteries. If you think about it, water systems are one of the one I guess industry that has large batteries that they can take advantage of. And so if this is a typical storage tank where you have your fire, you have your emergency storage, but most of the tank is actually designed for equalization, they call it. But that's where you can use the tank as a battery. Now most operators, they'll keep the tank completely full because that's their job, is to keep water in the system. And that's the last thing you want to see is their tank going empty. So because of that, they try to keep their tank completely full, and they don't take advantage of the equalization storage, or in other words, the battery. So here's an example of a water system. The dark line is their their water use over a day period. We start at midnight and we go to midnight. And this is one day, and you can see where they peak, and then the water use goes down. So this is a typical Utah where everybody's watering at night. And the dashed line are their sources meeting their peak. So this is a real system, and this is what they did before optimization, where they would ramp up their pumps to meet that peak and not take advantage of their battery. So after talking to them, we got them to use their sources more consistently. And the difference between the dashed line and the solid line is the storage. So in this area is where the storage is being used. This is where the storage is being filled back up and used again. So there's a lot of volume or area between the curves. And as you can see before, there was very little usage of that storage. So here's just a quick example of another real system where here they would use loading. The pumps would turn on, fill the tank, and it would cost them $274 a month. This is a very small pump, but $274 a month to do it this way. And after changing to a more sustainable way, removing the loading, their bill went down to $74. So we're using more of the storage tanks, and the source is feeding the system at a more constant rate. So the other common thing that I see in systems, especially here in Utah, where we have typically the oldest source in the city is the springs in the mountains that are coming down, and the city's always taken advantage of that head or that the pressure that provides into the system without having to pump. But over time, like you can see that in Orem and Provo, where they've gone up higher on the foothills, and so they've had to pump up there. So a lot of times the developer will put in a pump station, but in reality, there's opportunities that we can short circuit this process where we don't waste the energy and take it directly to the zone, and so we eliminate a pump station. Here's a good example of this is actually a real situation here in Utah, where here's one water system. They would reduce the energy down to another water system, pump once, pump twice, and put it into the third water system, who would then pump it, and then reduce the energy down to feed these people. In reality, this head is high enough to feed these people directly. If you do the math, this versus this is dramatically different in energy intensity. Leaping is another common one. Again, developers, they like to come in and put in one tank and one pump station to serve a new area because it's the lowest upfront cost, but it's usually not the lowest long-term cost. So if we pass the zone or bypass the zone, pumping all this water that goes here up to the higher zone and then reduce the pressure, reduce the energy, then that's an opportunity to save energy where you can pump the water directly to a water system. Again, another common situation. Or you could do it in parallel or in series. So looping, this is one of the first things that I actually saw in water systems when I started modeling, is where you have a zone, pressure zone, or an area that you serve customers, and then you pump water up to a higher area. This is very common where a water system will pump up there, but they'll also have valves that reduce the pressure back down to the same pressure in the lower zone. And it actually is a common situation where people will complain about pressure. The operator will raise the pressure setting at the PRVs, and you'll get this situation where water is actually pumping in circles without it actually being used. So it's just being used to proper pressures. So the way to stop that is set the PRV at a correct pressure to stop the water from going in circles. And I have a really quick example of this. This is actually North Salt Lake. This is the top of their system, and here's a tank up here, and here's a pump. And so when we went, and actually this goes down the hill here, and they have lots of pressure zones, 1, 2, 3, 4, 5 pressure zones, where they pump water all the way from down here to the top of the city. And so we actually showed this example to the city council and the engineers to show them what was going on. So I'm going to trace where this water goes, put a little Kool-Aid in this pump station, and this pump station is triggered by the level in the tank. So the level in the tank gets low enough that the pump turns on, and here goes the water to fill the tank. But what they didn't realize is that water kept going down, and within 1 hour, this water was coming back to the intake of the pump. So they're actually pumping the water that had just been pumped an hour before, and nobody was using that water. That energy was being wasted through what they call pressure reducing valves, or PRVs. But it got even worse. If you trace that water, we're tracing the water that went through that pump station. It's actually falling down the hill, falling down the hill. It got all the way to the bottom. And then it would pump back up. So this was a common way of how they operated the system all summer long. So this is after. So all we did was we told them to change the PRV settings. We gave them the actual pressure settings because we used the model to determine those. It took 2 guys about 2 hours one afternoon. They switched it. And then this was the result. So the tank would call for the water, and it would go down to the areas that it needed to serve, but it never got back to the pump station. So zero pumping in circles versus, well, here's the measured result. Basically, there were 50% of the water was just pumping around in circles. So ever since that one afternoon, they've now reduced their energy demand by 50%, almost 50%. And so that represents 1 million kilowatt hours, which is crazy. And even to improve the story, because they were pumping in circles, there was lots of pressure fluctuations, people complaining, and after they fixed their settings, the complaints went away, operators were more happy, the city was more happy. And so this is, again, a win-win situation all the way around. Last one is leaking. Obviously, when water is leaking out of the system, that's energy leaking out of the system. So if you have 30%, 40% water loss in your system, you have a 30 to 40% energy loss that you could reduce. Every unit of water, it takes energy to move it and to deliver to the customer. And so it's a direct relation. So really quickly, I'm going to give an example of the Logan City project. So Logan City, that's the home of Utah State. There's lots of engineers at Hanson Lewis from Utah State, and we get teased because we're from BYU, but we're changing that. Population about 50,000, about 10,000 metered connections, 190 miles of pipe. They have one very large spring, and they've added 4 deep wells to their system. So they were facing some problems, high pressures. They were having lots of water breaks because their system fluctuated in pressure quite a bit. Their pipes are old. They had high pumping costs, and they were always reactionary, running around fixing the system because it's getting old. So they hired us to develop a new well because they thought they were running out of water, and they hired us to design a new transmission line. But in the end, we asked them to take a step back. Let's do some hydraulic modeling. Let's do an audit of the water and energy use. And in the end, we decided instead of the well, which we figured out they didn't actually need, and instead of doing a transmission line, let's create a new pressure zone. Let's retrofit some pumps. Let's do some minor piping, upsizing, and learn how to operate the system more efficiently. So, let's set this up. So again, it's similar to North Salt Lake. It's low elevation down here and gets higher elevation. So their system is set up that they have basically one place where they have a storage tank that feeds most of the city. They have a large spring. It's called DeWitt Spring. That's in the canyon that comes down, and that was the historic original source of water for Logan. and then they've added wells to their system. So they have wells that pump back up to the tank when the tank gets to a certain level, and that's how their system is set up. So again, we did some hydraulic modeling, and what we showed them is that, again, we're tracing a well. This well was called to turn on when the tank got to a certain level, and we put some Kool-Aid in the model to see where the water was going. And 100%, even though the water was being called by the tank, they just assumed, well, the tank was filling up because the pump turned on. But 100% of that water was going down in their system, not going up. And this is the pipeline that they thought was out of capacity. They needed a new transmission line, and they weren't keeping up, so they thought they needed a new well. But in the end, what we convinced them of is to create a pressure zone to reduce the pressure down here, and then reduce the heads of these wells, which automatically is an energy savings. And we'll take that water directly to that pressure zone, thereby saving energy and eliminating the need to deliver the water all the way up here and letting it come down at peak or rush hour. So you can think of pipes as roads. There was a lot of competition at a certain time that they thought they were running out of capacity. So here's the new well that eventually will go online. But when it does, we're going to put a tank at a lower elevation that serves this area directly, so that these wells will never have to come up here, and we can keep the water at the lower elevation to serve this community. So in the end, it turned out to be a great project. These are the results, and we knew this was happening because we calculated it, and we modified the pump so we knew how much energy would be used after the project was implemented. This was an interesting one that we didn't anticipate, but because the pressure was dropped in that lower zone, less water leaked out of their system. So if you can think about it, they have old pipes, water is leaking out all over the place. If you reduce the pressure in the same amount of time, less water is going to come out of those pipes. And so they actually saved this amount of water, which actually was added to the energy savings. Because again, water lost out of the system is energy lost out of the system. So that was a bonus 17%. Plus, they're using less of another scarce resource, water. And then this was their other exciting thing that they were excited about, is that they had 40% less main line breaks because they were able to control their pressures better, so those old pipes weren't being stressed as much. And before, they had 2 crews, almost 20 people, running around fixing pipeline breaks. Afterwards, they basically took 1 crew off of mainline breaks, and they were doing preventative maintenance, which they really appreciated. So this is their list from a presentation that Logan City did. But these were their benefits that they identified. Less water wasted, less energy and money wasted. Citizen complaints dropped because there was less pressure fluctuations and better pressures. Preventative maintenance was occurring, crews' attitudes improved, safer working environment. So if you can imagine, with that 1 pressure zone, it actually got above 200 psi down at the bottom, which is actually quite scary. And then eliminated the need of a $3 million transmission project. They'll never need that because they thought of a new way of delivering water that's more efficient. And then it postponed the construction of a new water source. We actually did develop the well. It's ready to go, but even to this day, it's not equipped because they figured out that they didn't really need the source, but it's ready to go. So, in the end, there's this energy-water nexus that's really been quite ignored by the water, drinking water community, and the sewer-side wastewater, the whole water cycle. And it's being recognized now as an opportunity, a major opportunity to save energy and to make water systems safer and more sustainable. So here's my little Venn diagram to get that in your brain. So we have water quality. You guys are learning about that here. Hydraulic performance, hopefully you're learning about that. But energy efficiency is becoming important. like mentioned in my bio, I'm teaching a class at the University of Utah about designing water systems and using hydraulic modeling. Let me tell you, that's a tool that will be very valuable to you in your career. Even if you don't learn it here, you're going to learn it if you're into designing or analyzing water systems. And more tools like this to help engineers make better decisions in our area of expertise. So system optimization, I think, is one example, but as engineers think smarter and identify ways to be just as safe for the facilities that civil engineers are designing, we can also find ways to be more sustainable, less wasteful. I still fight engineers in my own company who want to design for a certain safety factor or do it a certain way. But there's always a way. It might cost a little bit more, but in the end, it'll cost everybody less to design more sustainable. And so that's my presentation. And hopefully you guys can learn from this and think of ways that are outside the box. Learn the basics, but start thinking about ways you can make civil engineering better. It's an old engineering field, but it can be still improved upon. Thank you. Any other questions? Yeah.
So one thing I was thinking about, does your company ever receive opportunities to work internationally with these things to help perhaps some humanitarian projects?
Absolutely. Yeah, in fact, all those, the national and the world organizations that are looking at inefficiency in water systems, they actually started in third world countries because they thought that's where it was, the opportunity was. But then they started looking inside the United States and seeing that we were just as bad. So yeah, I've been to Saudi Arabia. They're very similar to us. They use a lot of water, a lot of energy, but this is universal across the whole world. Absolutely. Anybody else? Great, thank you.